I don't know.
Okay, let's get started. There's a new homework assignment, and there's also an exam one next Thursday. What? Exam one? Yes, there's an exam one next Thursday. So we'll go over the homework assignment first, which is also due next Thursday. And I think this homework will help you prepare for your exam. So we'll take a look at the homework first, and then I cannot disclose the solution to the homework that is due tonight because, well, it's due later today, right? If I disclose the solution, that means I have to stop, people from turning in the homework at this point. So let's go to the website, and you should receive an email from me at this point already about certain things, like you have to follow the instructions of the homework assignment. Because if my tool doesn't work directly and I have to manually intervene to grade your homework assignment, I'll take off 1/2 of the point values. It really should not be that hard to follow the instructions, right? No? Yes?
If I tacked on extra comments at the very right where you had the comments at, would it affect the script?
It should not.
So I should just start from blank and just redo it?
It should not, because my comments, because my script is going to look for the label checkpoint or check here.
Okay.
So if you don't change the location or the name of the label, it should still be okay.
So comments will affect
Right.
Awesome.
Yeah, I can understand why you want to add additional comment, but as long as it doesn't move the lines, as long as it doesn't change the instructions, it'll still be okay.
Okay. So even if there's an extra line of comments stuck in there, it should be fine.
Right.
Okay.
Exactly. All right. This is all being recorded, so if you need to review this, you can review it. Those are all the things that are slow. Something is chewing off, all the I/O bandwidth, and I still cannot find out which process is killing my I/O bandwidth in this case. All right. Let's go to this class. And for those of you who realize, hey, I did not follow the instructions exactly, there's still time to turn it in again. Okay, it is due at 9:50 p.m. tonight. So after the class, you still have 80 minutes to redo it and make sure you turn in the right thing. And people who are missing from today's class obviously may not benefit as much from the instructions.
I almost missed that last instruction. Run this command in the directory that find it resides.
Okay, so this is what I sent to you by email. So whatever I post in the news forum is also sent to you by email. Some of you probably have read this already on your phone because as soon as you get your email, it is forwarded to your phone and you can read it on your cell phone. But in case you don't have access to your email, I'm just going to read this first. Please check your submission of Find It to make sure it is done according to the instructions. The instructions are very specific. Yep.
One other question. I, in the process of doing this, created a whole bunch of extra backup copies of Find It, and their names slightly different.
That's fine.
But if they're included in the tar file.
My script will only
looking for the
use
one.
find it dot lowercase s. So if you have additional files, it doesn't bother. The instructions must be followed 100% so that my grading script can process your submission. Remember, this is a pretty big class. If I have to manually grade every single submission, it's going to take a long time to finish this. Now, I will look at the code, but that's also part of the script. It will actually display the code, so I can actually do a visual, inspection of the code before it goes, to compile, assemble, link, and run the program. If it is not, according to my instruction, I will take half the points off if I have to do something manually to grade the assignment. So that means, you can deviate to a certain point as long as my script can still pick it up and grade it automatically, it's okay. But if it is something that my script, that causes the script to fail, and cannot pick up your submission, then I'll take off half the points, which is 5 points out of 10. Yep.
Can you give a specific example in which the
Like the wrong file name uploaded, like find it with a lowercase I .tar.gz. Like the tar command was not run, according to my instruction, or you did not use do your homework or tar it in your own the homework assignment folder. So instead you're using user or root. Okay, so that would cause problems too. So things like that. Basically things that will affect mechanically how my script is going to pick it up. Is this kind of go ahead.
You said not user. What
You should be doing this in your homework account, which means it is an account with your last name as the first part of the account. Yeah. How do I check that I turn in my homework according to all these instructions? That's the next question. You can download the tar.gz file back to your PC and then use 7-zip to inspect it. If 7-zip, inspect your folder or inspect your tar file, and it says something like, okay, there's a home folder first, and then under home is your last name. So in my case, it's AUYUNG. Under that is find it, and then under that we have to find it lowercase s. Then this is okay. This is the correct hierarchy of file folders and files. If 7-zip doesn't tell you that the directory architecture is like this, instead it is more like this, then it is not correct. Or if it looks like this, it is also incorrect. Or if it's like this, it is also incorrect. Is that okay? So I think I have enumerated most of the common mistakes that people can make, okay? And the submission file itself also has to be findit done .tar.gz. Not findit.gz, not findit done.gz, not findit done.tar, okay? So it has to be specific. Is that okay? And you have, 80 minutes after this lecture to double check and fix it, anything if you need to fix it. Is that okay or not? Is this kind of thing important, or am I just being picky? Well, think of this as a work environment, okay? In a work environment, and you are required to follow certain rules to turn in a file so that some other computer can do the job automatically. Is it kind of important to kind of follow the rules and the instructions carefully? Or is it just like, well, I can just kind of use the name that I choose, and someone on the other side will figure out how to use this file. It can cause problems, okay? If you are at work and the machine on the other side can automatically do something, but you have to follow certain rules to create your file first. So you have to kind of be able to follow instructions exactly in the field of computer science. I don't know anything about art, so maybe in an art class, you don't have to follow instructions as exactly. Is that making any sense? No, kind of?
When I standardize your inputs, you can just create really fast.
Well, that too, but I think it is important to be able to read the instructions and follow the instructions exactly. And 5 points out of 10 from the first homework assignment is not really doing a whole lot of impact down the line, because there'll be a whole lot more points later on. But I think it is important to really get into the habit of following the instructions. Okay. Are there any other questions? No questions? Did I mention that the PWD has to be enclosed in back quotes and not forward quotes? And how many times have I mentioned that, including this time? I don't know. I have to watch my own screen recording to count exactly the number of times. But I know it's more than 1 or 2. All right. So let's take a look at Find It version 2, okay, the sequel to the first. I pretty much just copied and pasted most of the instructions because the instructions is not all that different. So we'll go take a look at this one. It uses the same method. So what you want to do is to download it into a folder. I'm just going to put it into my download folder. And then you go to a command prompt and do an unzip on that. Oh, not unzip, tar. So in this case, it's in my download folder. It's called findit2.tar.gz. And once again, it decompresses into a folder with a file inside the folder as the starting point of the homework assignment. So we'll go ahead and take a look at the new homework. And here's your new homework assignment. It looks kind of similar to the other one if you just read the instructions under the underscore start. Okay, let me turn on line number so I can refer to the line numbers. If you just look at line 9, the instruction says you can only specify values where the question marks indicate. Do not move any instructions, add any instructions, remove any instructions, or change anything other than the question marks. And I had a typo. Question? Okay, question marks. Okay, so that's the question mark. So that means there are only 3 things you can specify here. It's here, here, and here. Those are the only 3 things you can replace with specific values. At the point of check here, the label, e dx in this case should have a value of this particular value. Does that look like a octal number, a decimal number, or a hexadecimal number to you? It's a decimal number because it doesn't start with a 0 at all. Okay, if it starts with a 0 without the x, it is a octal number. If it starts with 0x, it is a hexadecimal number. So the first thing you might want to do is to look at this, in a byte, byte by byte, format. And then what you want to do is to find a way to anchor, particular registers. You have to look at this instruction here, and then find out, how do you fix, the value of, let's say, edx, and then how do you fix the value of eax, and how do you fix the value of ebx. I cannot guarantee there's only one unique solution, but I know there is at least one solution. So if you find, if you, compare notes with another student and you say, okay, how do you have your own solution, and you ask the other person, what is your solution? If the other person has a different solution, it is possible, okay? But I'm just saying that there's at least one solution. It is not undoable. Are there any questions about this? Yep, go ahead.
Are you using start label as base offset for that?
Yeah, there's nothing wrong with it. See, everything is under dot text. So, all the labels are defined in the dot text section. In other words, everything is using one single binder. Remember how dot text is like one binder and then dot data is like another binder? Since we're only using one binder, if you know, where L1 is like a bookmark on a particular page. Yeah. Underscore start is another bookmark of another page. So, you can...
You're allowed to use underscore start for other purposes.
Absolutely. Yep. Yeah. Underscore start only has one, particular special meaning to the linker, but other than that, it has no special meaning. It's really just a label, just like L1. All right. You're welcome. So what you need to do, if you have not studied the addressing modes, the first thing you want to do is to study the different the various addressing modes. If you have questions about the addressing modes, you can write simple programs to make sure that your understanding of a particular memory operand is correct. Okay, so I would not approach this until I'm really crystal clear about all the memory operands. Yeah.
Now, underscore start, does that reference the start by global or the start on line 8?
It refers to the definition on line 8. Line 2 dot global underscore start is a directive that tells the assembler that someone else may need to know this label underscore start. So the only thing it does is quote unquote export underscore start as a label so the linker can see it too. Because otherwise, like L1, which is not exported, then only code within this source file can see this particular L1. If you are linking between multiple files, all the other files cannot see L1. So underscore start is special only because it is exported. Other than that, it is really just only. Are there any questions for this particular homework assignment? I think this will really help with your exam one, because exam one covers pretty much the same type of material. Yeah.
Wouldn't you, like, as a standard with the creative production environment, would you want to do a label for each data type, or a not so-called variable, I guess, for each one that you want?
This is really just a homework. In other words, this particular program serves no real purpose other than making sure that you guys understand the addressing modes. But in a real program, you only need labels where it is needed. In this case, I cannot put labels where it is needed, because otherwise, that kind of defeats the whole purpose of the homework of trying to hunt for the particular bytes and the locations.
As a convention, though, you would never really do it that way, right? Hopefully.
No, but sometimes when your program has a bug of kinds, you can accidentally use locations that you're not supposed to. So being able to do the detective work, like, okay, I find this particular byte pattern over here, it is not supposed to be there. It's really helpful to understand how the memory is organized and be able to kind of backtrack your program and find out, okay, how did this get into here? So that's another purpose of this program is to really build up the skill set that will be useful later on in this class. Any other questions about this particular homework assignment? Yep.
Did you add in that last new line? Did you just add in that last new line?
Nope. This is in the tar.gz file, all the time. That's why I was kind of curious when you showed me the program in the lab, without that the line with ECX. Did you accidentally delete it, maybe? No.
I just opened it fresh tonight.
Because I only uploaded this program once, so I know it is not. There's only one version, as far as the server is concerned.
If I just added it in, it would.
You can just add it back to me. That's fine. Yeah. All right. Any other questions about this particular program? No questions. All right. Well, we still have Tuesday to ask questions about this. Okay, so. So for now, I'm going to quit this program and talk about the practice test. I will show you what how I asked questions last year. So that will serve as a, okay, so we'll save it into this folder. Pick a folder for today. So this is what I asked last year for exam one. Some of these I think will not apply to this class because we have not covered the add and the subtract instructions yet. So we'll go take a look at these particular programs. So we'll start with Q1A. Q1A, Q1B, Q1C, and Q1D are basically the same question, just different variants of the same question. All right, so this is question number one. Most of it are comments, to basically explain what you need to do. This is not a complete program. You have to replace two sequences of list-like instructions with cisp instructions using fancy operands. We cannot do this one yet because we have not talked about the add long instruction. You can see there are two add long instructions here. We cannot do this one yet. So we'll take a look at the second program. We cannot do this one either. Am I going really slow this semester? Yeah, we cannot do that either. And this is the last one. We can certainly do this one, can't we? In fact, doing this particular program is going to illustrate some of the techniques that you can use for your homework assignments. So this is really good. All right. in this question, I'm just reading on line 2. In this question, figure out the value of EAX after a sequence of instructions. To help you to the answer and potentially get partial credit in case the final answer is incorrect, explain the result or effect of each instruction. Okay, so let's go ahead and see what is going to happen here. What do you think EAX will contain after this instruction? Let me turn on the line number so we can refer to the line numbers. Here we go. So what do you think is in EAX after this instruction executes? Okay, I'll give you two choices. Okay, in this class, in a pre-test, review, I'll give you two choices. Does it have L1? Because remember, L1 is a label. It is defined to a particular value, which can be seen as an integer. So does it contain L1, or does it contain the 4 bytes starting at that location? The first choice or the second choice? Is that your final answer? It contains just L1, not the 4 bytes at L1. What kind of operand is this? It's an immediate operand. Is an immediate operand a memory operand?
No.
No, it is not. So that means we are not accessing memory. We are just copying the value of L1, the label itself, to EAX. Are we doing okay so far? If L1 is defined to 5, okay, then EAX ends up with a value of 5. Well, L1 is not defined as 5 because the way I define L1 on line 9 is it is the address of the first byte of that .int. Okay? Is that okay? All right. So I'll just go ahead and write this down, and you guys can formulate your questions. So in this case, after the assignment, EAX has the value of the label L1, but not the memory content at location L1. All right. The second instruction, what do you think is going to be in EAX after this instruction on line 13?
Same as L1? The same value as L1?
The same value as L1. Well, it is going to copy, in this case, how do you call the first operand? EAX in parentheses.
It's using the value at EAX as the address.
And then source. And then whatever is at the location becomes the source operand, right? So in this case, is that a memory operand? The first operand of line 13, is that a memory operand? It is a memory operand because it is grabbing the 4 bytes starting at the location where EAX is pointing to and copy those 4 bytes to EAX itself. Okay, which is perfectly fine. You can use EAX, in different ways. One as a source operand and one as a destination operand. There's no conflict here. All right. So after this instruction, what do you think EAX will have?
0, 0.
Sorry. Okay,
so
so
L1 minus 4, and I'm trying to count over.
So we are basically dereferencing, the location. So whatever is in L1, we are going to dereference it. So I'm using the approximation of a C operator here. What is at location L1? There's a little .int, right? And the .int says what? L1 minus 4. Okay, so that means after this operation, EAX is going to have the value of L1 minus 4. Not whatever is at the location L1 minus 4, it is L1 minus 4 itself. Are we doing okay so far? I will run this in the debugger so we can actually see what is going on when we go through this program. Is that okay? Kind of? Okay. The third instruction. The third instruction, once again, the first operand is the one that is interesting. It's not the second operand. The first operand is what type of operand? How do we call this type of operand? it looks kind of like an indirect operand, but it has a number in front of the parentheses. So we give that a particular name. What is it? It's a based operand. Okay, just based. There's no index or scale in this case. Okay, so it's a based operand. Is it a memory operand? Yes. Does it access memory? Yes. It does. And where are we copying from in this case? L1 minus 7 is the correct answer because I'm just adding -3 to whatever is in EAX when this instruction executes. EAX already has a value of L1 minus 4. So if you subtract 3 from L1 minus 4, it is L1 minus 7. That's the location that I'm copying from. Okay? What is at that location, L1 minus 7? Just looking at the code here, just looking at how I initialize memory, can we figure out what is at L1 minus 7? Well, let's try to do that, okay? So I'm going to try to, I will try to do this step by step. The least significant byte of this constant is at L1. L1 minus 1 is going to be this byte. L1 minus 2, oops, I take it back, I was wrong. L1 minus 1 is actually 0, 0. Because it takes 4 bytes for each item on this line. So there are 4 leading zeros that are implicit when we look at this. So L1 minus 1 is 0, 0. L1 minus 2 is 0, 0. L1 minus 3 is 0, 2. L1 minus 4 is 5, 0. L1 minus 5 is 0, 0. L1 minus 6 is 0, 0. L1 minus 7 is this byte here. Okay, that's the first, that's the L1 minus 7. So let me just kind of write it down here. L1 minus 7, if you dereference at that location, it will give us, the 2, 5. All right, are we grabbing just 1 byte? How many bytes are we grabbing?
4.
We're grabbing 4 bytes. Have I already mentioned those other 4 bytes? The other 3 bytes that that need to be copied here?
Yes.
Should I look at L1 minus 8 or should I look at L1 minus 6?
6.
Minus 6 because we are moving back up again. This is the starting point, so we have to copy everything from here and the other 3 bytes. So L1 minus 6 is 0, 0. L1 minus 5 is 0, 0. And L1 minus 4 is what? Is the 5, 0. Yep. So when you combine all of this, what do you think EAX has? So this is where, now that we have figured out what those individual bytes are, now that we are copying all 4 bytes into a 32-bit register, the little endian nature of the Intel processor becomes important because we have to figure out which byte becomes the least significant byte and which byte becomes the most significant byte. What do you think?
2.5 is the least significant.
2.5 becomes the least significant because according to the little endian convention, the least significant byte has the highest or lowest address. The lowest address. Okay. And out of L1 minus 7 all the way to L1 minus 4, which one has the lowest address? L1 minus 7, right? Because it has the lowest value, the smallest value, and therefore it has the least address. So when you look at this whole thing, then 5, 0 is the most significant byte. Then we have 0, 0, 0, 0 in between, and a 2, 5 at the end. So that means EAX should have this value when this instruction is completed. Yep.
Why are there 4 leading zeros?
Because it's a .int. Oh, which code? Okay.
Yeah,
in the homework assignment, I use .long. .long and .int are exactly the same thing. Okay. That's important because the homework assignment finding 2 has a .long instead of a .int, but it really means the same thing. So because it's a .int on line 8, each item separated by a comma is going to require 4 bytes to represent. Now 0250 obviously only need 2 bytes to represent, but I'm going to allocate 4 bytes anyway to represent the same value. So that means I just have to add the most significant part with 2 bytes that are both zeros. Because the whole thing is really just 00000250. Okay. All right, so let's take a look at the next instruction here. I'm copying 2 bytes in this case. How do I know I'm copying 2 bytes? Move W, the word in the instruction means, I'm copying 2 bytes or 16-bit. I'm copying from the location L1 plus 5 to AX. So let's go ahead and figure out what is at those locations. Okay, so first we want to look at L1 plus 5. What is at that location, L1 plus 5? Let's try to figure this out. Okay. This line is going to take L1 all the way to L1 plus 3, because that will account for the 4 bytes of this dot int. So that means that L1 plus 4 is going to be this byte. L1 plus 5 is 00. Because as a dot word, it needs 2 bytes. So the 25, it will take up the least significant byte, but there's a more significant byte of 00 that is not displayed, when I look at the number as a hexadecimal number with only 2 digits. Is that making any sense so far? Okay. So L1 plus 5 is 00. And in this case, since we are moving 2 bytes, so we also have to look at the next location, which is L1 plus 6. L1 plus 6 is the least significant byte of the next dot word, which in this case is 00. In other words, we are talking about 00 from the most significant byte of this dot word and the least significant byte, which is also 00 of the next word, the next 16-bit constant. Are we still doing okay? No?
You over that?
Okay, go ahead.
Wouldn't L1 plus 6 be 25?
No, because the 25 is the most significant byte, so that would be L1 plus 7. L1 plus 7 is that 25 on line, the second item of line 10.
Wouldn't it be the first item 25 because it's the word and there's 2 bytes?
The first item?
Okay. At L1, the int right there is the first 4 bytes, and then the L1 plus 5, would that be 25? And then the L1 plus 6, would that be the 00 in the first item?
No, not really. Okay, maybe I can use another way to illustrate this. Okay, so let me finish this first. Before I run it, I'll use a spreadsheet to basically show the same thing. Okay, so the next instruction is putting L1 plus 7 into AH. We just visited what is L1 plus 7. L1 plus 7 is 25, and it is this particular 25, which is the most significant byte of the second item of line 10. Okay, but the question now is, what is EAX at this point? Well, AX turns out to be the least significant 16-bit of EAX, so that means the most significant portion is unchanged, and then the least significant portion is 0000. This one is going to change AH, so that means we are changing bit 8 to bit 15. So that means this part is the same. This is the only part that got changed, and this part is the same again. Are we still doing okay? Because AH is bit 8 to bit 15 of EAX. AX is bit 0 to bit 15 of EAX. So we are just changing parts of EAX with the instructions on line 16 and line 17. So the correct answer in this case, by this time, EAX should have a value of 0x50002500. So we'll go ahead and take a look whether this is really the answer or not. Okay. But before that, I'll use a spreadsheet to basically talk about the same thing. Because the key is how do you know what are the bytes in memory. That really is the most important part. So I'm going to use spreadsheet, because a spreadsheet is really handy for this kind of thing. It's a table, and I can do calculations if I need to. All right, so this is where I'll put an L1, and this is going to be the offset, and this will be the actual byte value at that location. All right, so let's start with the first byte in dot text. What is that going to be? It's the least significant byte of the first item of line 8. What do you think that should be? It's 25, right? It's not 25 because when you say 25, it is implied to be base 10, so this is just 25. What about the next one? Right? What about the next item? The least significant byte of the second item on line 8. 0, 25, 0, 0. And here we are up to the least significant byte of the third item of line 8. We got 5, 0, 0, 2, 0, 0, 0, 0. And now we have 4 bytes, together it becomes L1 minus 4. So in this case, I cannot really show you the individual bytes because it all depends on where the linker or where the linker decides to put this. Yep.
So the ordering actually matters there.
Sorry?
The ordering.
The ordering?
Like the ordering of how you calculate the word, dot word. It actually matters to how it gets memory.
Yes. All right. But this is a good time to indicate where L1 is. L1 is right here. It is at the location right after the last item on line 8. Okay? And the second column, with column B, what I want to do is to say this is L1 plus 0. And this is going to be L1 minus 1, minus 2, and so on. Let me see if this will work. Yep, it does. Nice. Okay, so L1 plus 0, plus 1, plus 2, plus 3, these 4 bytes combined is going to represent the value of L1 minus 4, because that's what the directive is indicating. So I'll just combine these 4 into one single square, which means these 4 bytes is basically just L1 minus 4. But then I still have to indicate the offset. This will be offset 1, offset 2, offset 3. And I'll change the format of these cells so that it's clear whether we are adding or subtracting. And I think, let me see. If I want to force negative number spread, no, that's not what I want. So we'll go ahead and try user defined. Yep, there we go. Oh, no, that's not How do I force the sign but without doing the weird thing?
You can define them differently for
Just like
pluses and minuses.
Don't select the whole column. Select the positive values.
Yeah, but it should work with that too. You're saying just change this portion, right?
Yeah.
But that's kind of like saying I don't know how to do it the other way, which I don't like. All right. Well, that's I'll not focus on that for now. Okay. What about the next location? Yep.
I have a question. What if instead of at the label L1 is you're defining an int with the value of L1 minus 4? What if the value was just L1?
Then it is just L1.
What would the value be?
Then this will be just L1. There's nothing wrong with a location, a 4 byte, 4 bytes in memory turn out to be the address of itself. That's fine. Is that kind of okay? Okay, it's okay. In C,
The value would be the address?
it turns out to be the same thing. In other words, okay, let's look at this in C and C++. So you have a void pointer PTR, okay? And this can be global. Let's just say this is a global variable, okay? So in some code, within your program, you can say PTR equals to the address of PTR. there's nothing wrong with this, particular assignment statement in C.
Would it be like pointer arithmetic?
There's no arithmetic here. In this particular case, when I say PTR equals ampersand PTR, it really is just saying, PTR has the address of PTR. And no typecasting is really needed here because anything can be downcasted to a void pointer. Is that right? I think so. Void pointers are special. All right, so are we still doing okay so far with the questions? Kind of. This really makes your homework assignment look like a walk in the park, doesn't it? Well, I would disagree. Okay, so what is the next one? At offset 4, L1 plus 4, what is at L1 plus 4? A 2, 5. Okay, very good. So hexadecimal, oops, wrong side. 2, 5. And then the next one, 0, 0. And then the next one, 0, 0, because it's the least significant byte of the second item on the dot word line. And then the next one, 2, 5. And the next one is 5, 0. And a 0, 2. So I'm just going to follow this sequence here. And this time I'll force the sign to have a positive. There we go. It's looking good. In other words, this is how memory is organized, with all the directives from line 8 to line 10. Is that okay so far? Okay. So when you look at the first instruction will make EAX a pointer, basically. And EAX will be pointing to this location. The second instruction is saying, okay, let's dereference the pointer, copy whatever is at the location pointed to by EAX, and copy that into EAX. So that will basically copy this number into EAX. As a result, EAX ends up with a value of L1 minus 4. The third instruction is saying, let's go to kind of where EAX is pointing to, which is L1 minus 4, but let's go back 3 additional bytes. L1 minus 4 minus 3 is L1 minus 7. L1 minus 7 is this particular byte, but because it's a move long instruction, I want to copy not only this byte, but the other 3 bytes as well. When you copy multiple bytes into a register, then you have to think, okay, what does little endian do to this particular move instruction? Little endian means the least significant byte is the one at the lowest address. The one at the lowest address is the one that I'm highlighting right now, which is the 2, 5. So you have 5, 0 as the most significant byte, 0, 0, 0, 0, 2, 5. So after the third instruction, after the instruction on line 14, EAX ends up with 5, 0, 0, 0, 0, 5, 0, 0, 0, 0, 0, 0, 2. Are we still kind of doing okay so far? The other 2 instructions, on line 16 and 17, once you have this table, they become kind of really, trivial. Because L1 plus 5, you just look up L1 plus 5 is 0, 0. But since this is a move word instruction, I'm copying 2 bytes. So I'm copying these 2 bytes to overwrite the least significant 16 bits of EAX. And that's why, in this case, EAX, just have the lowest 4 hexadecimal digits all, zeroed out. And then the last instruction is copying a byte because it's a move B instruction. And we are copying from L1 plus 7, which is this byte, to AH. AH is the second least significant byte of EAX. So that's why this location is changed in EAX. Is that better? I mean, once you have this little picture here, does it help? So this is something that you might want to do with your homework assignment too, because your homework assignment is kind of like the reverse of doing something like this. This one shows you all the numbers and everything, all the instructions are defined. You have to figure out what is actually going into EAX in this case. Your homework is the reverse. I tell you what EDX should become, and you have to figure out what values you have to put into the registers. So it's just kind of like the reverse of this. But you still have to do basically the same thing. You still have to understand how memory is laid out. You still have to understand little endian, and GDB as a tool can be extremely helpful too. Are we still doing okay so far?
I'm missing one, and you went over it twice, but I missed it both times.
Go ahead.
For the line 15, when we
Line
get
15?
50000002, can you count that off for me one more time?
It's 50000025.
Yeah, so we get the 50 from L1 minus 4.
We get the this is copying from L1 minus 7, right?
Minus 7.
So
okay.
L1 minus 7 is the first byte of the 4.
Okay.
So we are copying these 4 bytes.
Exactly. So
Out of these 4 bytes, the one with the lowest address is the least significant byte. So the 25 is my
25
least
first,
significant
yeah.
byte, and then the 00 becomes the next, 00 becomes the next, and the 50 becomes the most significant byte.
okay.
But when I write it as a 32-bit number, I write it using 50
Oh.
first because it is the most significant part.
The window was over, and I didn't see the 5 on the end, and I was
Oh,
getting very
okay.
confused.
Sorry.
That makes sense now.
There you go.
Okay, that's good. No, we're all on the same page now.
Okay. Excellent. All right. Any other questions?
What did you change? What did you just change?
I didn't change anything. I was just moving the screen because the spreadsheet was covering a part of that number.
Gotcha.
All right. Any questions? I hope I didn't make a mistake because I really do not remember the correct answer to this one. In other words, if someone stop me and say, "Give me the answer," I don't remember. I really do not. You can read my mind. You may find something that you don't want to find out, but but the answer is not there. All right, so let's go ahead and test run this program. AS gstab -o q4a.o q4a.s ld q4a q4a.o. Oops. Yep. Okay. gdb q4a. It's the program. Let's do it step by step. So let's go ahead and stop at the first instruction. Run it. This is the first instruction. So we want to take a look at EAX first. It has an initial value of 0, which is not very useful. And then we want to print out the label L1. And remember, when you use print, you cannot just say print L1 because the debugger actually will try to dereference it. So you have to do a dereference, like ampersand. But we now know that L1 has a value of, the label itself has a value of 8048060. So how do I know that really is the address of L1? How do I confirm that? Well, we can use X, right? We can use X to dereference the 4 bytes at that location as one single hexadecimal number and make sure that that value is this number minus 4. Okay, so that's one way to verify that our understanding of what is at location L1 is correct. So we do an X for examine. One thing, the one is implicit, it doesn't have to be specified. It's a W because a word in the debugger is 32-bit. I want to display as a hexadecimal number, and it is just at L1. Okay, so what I should be seeing here should be 4 less than this value. Okay, this value should be 4 less than this value. If you know your hexadecimal number, that's pretty clear right away because a C is a 14, a 0 is either a 0 or a 16. So 16 minus 12 is 4. Okay. If you're not convinced, you can always copy and paste and do a subtraction and print, the first number minus the second number, and that will give you 4 as well. Okay. So that means our understanding is kind of correct. But we also want to do something that will give us something that looks like this. Okay. All the bytes, all lined up, so it's easy for us to figure out which byte has which location has which byte. Okay, so we can do something like this. Okay, I'm just doing this with 8 first, and then we'll modify that to become more useful. Okay, so I can do something like this. It's basically saying, at location L1. In other words, this is the address. But if the address so happens to map to a label that is close by, the debugger is friendly enough to basically say, oh, you know what, this particular location has a name and it's L1. So it's really handy. So at that location we have 5080, 5C, 804, and 8. These 4 bytes, combined is L1 minus 4, and then we have the 25000025. And if you look this up, we have L1 minus 4, which are the first 4 bytes, and then we have 25000025. So it's kind of working out pretty good. But we want to do the entire dump all the way from L1 minus 9 all the way to L1 plus 9, okay? Because that would be pretty handy if I can just look at everything in one single dump. So we'll go ahead and try to do that. How many bytes do we have? Oh, actually, I scrolled off the screen a little bit. I want to do it from L1 minus 12 all the way to L1 plus 9. And this tells me there are 22 bytes. So we'll go ahead and examine 22 locations. Each one is a byte, each one printed out in hexadecimal. We want to start at L1 minus 12. And there we have it. And now we can try to match up those numbers to the spreadsheet. So I will display these numbers on one side and look at these numbers on the other side. So we got this 25 being this 25, 0, 0, 0, 0, 0, 0, 0, 0, 25, 0, 0, 0, 0, 5, 0. So this 5, 0 is matching this 5, 0 here. 0, 2, 0, 0, 0, 0. These 4 bytes together is L1 minus 4. And then after that, we have 2, 5, matching this 2, 5 here. 0, 0, 0, 0, 2, 5, 5, 0, and 0, 2. In other words, the debugger is handy to have, but we should be able to do this without the debugger. Yep.
How did you come up with minus 12, L1 minus 12 on the debugger?
In the debugger, why did I pick minus 12? Is that the question?
Yeah.
I chose minus 12 because that's the first .int definition. Doing it anywhere beyond that would not be very meaningful because it's not initialized by the directives. Yeah. Any other questions? Yep.
I don't get how you got from L1 plus 4 all the way down.
L1 plus 4. Okay. So L1 plus 4. Let me go back to the editor. I'll go ahead and look at the source code at the same time using a plain editor here. So we'll open up user Q4. That's right here. Okay. So this line will occupy the bytes at location L1, L1 plus 1, L1 plus 2, and L1 plus 3. Those add up to 4 bytes, right? So L1 plus 4 will be the least significant byte of this dot word. But the dot word is going to take up 2 bytes. So the most significant byte of this particular item is implied 0, 0. So that 0, 0 will be L1 plus 5, L1 plus 6, L1 plus 7, L1 plus, what is it? 8. And then L1 plus 9. But the little endian convention plays a very important role to lay out the individual bytes one by one. Are there any questions about this question or the answer? How I try to figure this out one step at a time. Yep.
So just perfectly clear.
Mm-hmm.
The first word and the second word are both equivalent.
No, they are not. The first word has 2, 5 as the first byte, 0, 0 as the second byte. This one has 0, 0 as the first byte and 2, 5 as the second byte.
Oh, I guess that's what we have written down. Yeah, never mind. Like this.
Okay. Well, they have the same 2 bytes, but the ordering of the 2 bytes are reversed. Okay, any other questions? Yep, go ahead.
So the dot int L1 minus 4, that's copying the address of 4 bytes before L1?
No, it is, okay, L1 is a label. Okay, in other words, L1 is, you can look at it as an integer. Okay, it's a symbolic name that maps to an unsigned integer. That's one way to look at it. So L1 minus 4 is nothing more than whatever the integer is minus 4. Is that okay?
I think you confused me more.
Okay, go ahead.
Is L1 just assigned a random value?
L1 is a label that is defined to be the current location in the dot text section. Okay. In other words, the other way to look at this, oh, okay, this is not VI. You know, I was using the VI keystrokes. You can see. Okay. So in other words, I could have done it the same way, saying L1 equals dot, then use the dot int definition. Is that better? I mean, because this is really what a L1 colon is really doing. Okay. So L1 is defined to be the current location in the dot text section, which is quote unquote an address, but the concept of an address is a high level concept. As far as the assembler is concerned, it is really just the current location, which is an integer. Okay? So when we refer to L1 minus 4 on the line of the dot int, it's really just saying, okay, look at the definition of L1. Okay, L1 is some location, which is an unsigned integer, or you can look at it as an unsigned integer. So we just calculate L1 minus 4, which is another integer, and we make those 4 bytes represent L1 minus 4 as a 32-bit integer. Okay.
Earlier before you said like the first word, so like it's because the word is implied 16-bit, it would just like tack on extra,
So ask the question again.
First word is added because it's the word is added.
The dot word are 16-bit, but the dot int is 32.
So it's similar to the second word. Well, not right now, but earlier, but similar to the second word, but like it just tacks on extra zeros. You said.
Oh, okay. The extra zeros. There are multiple places where there are additional zeros, the leading zeros. Like the first item of the dot int, which is only 25. Now, if you want to represent the hexadecimal 25, you only need 1 byte to represent it. But because it is in a line that is using a dot int directive, it means every single item will be allocated 32 bits or 4 bytes. How do you use 32 bits to represent 25 in hexadecimal? Well, easy, right? You just have additional zeros to the more significant bits. So that's why the first item of the dot int ends up to be 00000025 when you read it out as a 32-bit number in hexadecimal. But in terms of memory organization, it is 25 as a byte, 00 as a byte, 00 as a byte, and 00 as a byte. All right, that's good. Any other questions? No other questions? All righty. So that's really the only question that I can go through, because all the other questions have instructions that we haven't talked about yet. So that means you will get some additional questions this time about binary add. Do you remember binary add? That's a topic that we talked about when we talk about the architecture itself. So we'll have questions about half adders, and also how do you generate the carries when you perform binary add. Kind of like your first homework assignment with a spreadsheet. Okay. Any questions at this point? Yep.
So, about halfway up on that GDB screen.
Is
where
it
you-
scrolled off already, or
No,
is it
you
still
have
here?
it. You're down about 5 or 6 lines. It's just right there, and then left. Yeah, you're just about to highlight it. So that 804, 8060, that's just an arbitrary value that's just.
It's
been
not
assigned to
arbitrary.
L1.
That value is determined by the linker. In other words, the linker is the one, who decides, where do we start dot text, okay? And that's, just so happens to be, well, that's not dot text, the beginning of dot text. This is actually after the dot int, constructs. So, it's already 12 bytes, down from the actual beginning of dot text. Any other questions? Yep.
Yeah, could you open up the program again and go back to
Absolutely.
Now, this is about line 10, the L1 minus 4.
Okay.
Why is that interpreted like you're using it as an address, but then you're giving a value at that address?
It's a page number, right? Okay, let's look at this, in using a binder, analogy. All right. So the dot text is one binder, and the dot data is another binder. All right. In the dot text binder, every page is a page number. After the linker is done with its job, the pages have absolute numbers. Okay, they're no longer floating and say, okay, if the beginning of if the program is location 0, then I'll be at location 5. No, after the linker, they have definite absolute values. Okay, so in that case, you can look at the first 4 bytes to be page Okay, I'll start with 1000. Okay, so we'll start with page 1000, page 1001, 1002, and 1003. That will account for the first dot int item. And then 1004 to 1007 will account for the second item, and so on. So using that analogy, the dot int for L1 minus 4 is going to start at 1012, location 1012, right? So that means if I want to define the label L1 as a bookmark, it's bookmarking location 1012. Is that okay so far? Okay. Well, you can look at 1012 as a page number in a binder, and it makes sense. Okay, 1012 actually has some content in it, and it is one of the content that you have access to. But 1012 can also be seen as just a number, 1012, right? So what is 1012 minus 4? 1008. And I'm just saying that on page 1012 to 1015. I want to use those 4 pages to write down the number 1008. Is that doing okay so far? Okay, so that's basically what it is. In other words, L1, can be seen, it's really just a number. Internal to the assembler, it really is just a number. And you can use the number in different contexts. In some cases, you can use it as an address, so you can go to the location and then you do something about the content at that location. In other cases, you look at L1 and go like, oh, it's just 1012. It's just a number. You can add, subtract, multiply, divide, treat it as any other integer. Is that?
Yeah.
All right. Okay. All right. So do you think this little exercise has, is helping you a little bit with your homework assignment? Yeah, the homework assignment has some additional addressing mode, because it has the based scaled index mode, as well as just the based and also the indirect mode, which are also explained here. So the first thing you might want to do is to make sure that you understand the addressing modes correctly first by writing simple programs to basically prove that, yes, I think I understand how this particular addressing mode works. Because once you have confirmation that your understanding is correct, it makes it easier to work on the homework assignment. If someone does not have the correct understanding of the addressing modes and try to solve the problem in the homework assignment, that would just go to nowhere, okay? Because it's not going to work. So you got to make sure that you can confirm that your understanding of the addressing modes is correct. Does everybody know how to write tiny little programs to prove a particular point? No? I'll write one program like this, and then you guys can use that as an example to write the other programs. In this class, I have to say, it is extremely important to be able to come up with simple sample programs to prove that your understanding is correct. Okay? It may seem like a waste of time, because you're spending like 5 minutes to write a tiny little program, and it serves no purpose other than saying, oh, so my prediction of what this program is supposed to do is actually correct. The debugger confirms that. So it seems like a waste of time, but it does serve two important purposes. One, the debugger does not lie. Okay? It's better than asking someone and ask, what do you think this program is going to do? Because a person can make a mistake, misinterpret the instructions and so on and so forth. But when you run it in the debugger, that really is the real deal. Okay? And the second thing is, the more you use the debugger and the command line commands, the more familiar you are with all those things. So it will just help speed up additional homework assignments later on. Okay, so I'll go ahead and write one little program to prove, a particular point, that my understanding of a particular addressing mode is correct. Okay, so I'm gonna put, okay, I'm just gonna call it a generic example program. And here's underscore start. And for this program, all I want to do is to make sure that my understanding of, let's say, the base addressing mode is correct. Okay, so I'm going to define a whole bunch of bytes here. Okay, in fact, I'll just use a sequence. In other words, I know exactly what I should find at each location because the value of each location is implied by its position in the sequence. Okay. So I'm not trying to make this particularly tricky because I'm just trying to understand a particular point. So in this case, I'll move a particular thing into a register. So I'll put L1 into EAX, and then I'll move B, let's say, to EAX into BL. That's my program. And if you are not going to complete the execution of the program, you don't even need these instructions. But as a habit, I just want to make sure that my program has the right exit code. Okay, so I'm just finishing this program here. In other words, in this particular program, lines 3, 5, and 6 are the only meaningful lines here. It is only here to make one single point. Okay, I should be able to know exactly what will be in BL after I execute the instruction on line 6. That's all. It doesn't serve any other purpose in this case. All right, so I'm just going to tell myself, after the first line, EAX should have the value of the label L1, not the content at that address, okay? Whatever L1 is, I'm copying that to EAX. And then in the second instruction, I'm adding to whatever EAX has, but since I just initialized that to L1, that means L1 plus 2 is the address where I will grab 1 byte and copy that to BL. What is at the location L1 plus 2? Okay, this is at L1 plus 0, L1 plus 1, this is at L1 plus 2. So that means BL on line 6 should end up with a value of 0, 2. That's my prediction. Well, but my understanding may not be entirely correct, so I'll go ahead and test the program to see whether that really is the case or not. Assemble, link, and use GDB to help me, with this program. Put a breakpoint on line 5. Okay, so I can put a breakpoint at the very first line of the program. Just to confirm that EAX has nothing before, single step, look at EAX again. It has some content, but I want to know what that content really is. So I'm saying that it really should be the same as L1. So I'm going to print ampersand L1 just to confirm that they are the same. In fact, they are, because EAX has the value that is the same as L1 itself. So I just confirmed what is in EAX at this point. I single step the second instruction. I want to look at what is BL. BL has 0, 2, so that's exactly as predicted. So these will be the kind of things, this kind of program is what I would write when I study for a class like this, just to make sure that my understanding of some minor detail is correct. And I'll write plenty of these little tiny programs to confirm every single little point about assembly language programming. Yep.
I thought it took 8 bytes to store a label.
Sorry?
I thought it took 8 bytes to store a label.
Internal to the assembler, yes.
So then you copy it into
A 4-byte thing.
A 4-byte thing. So
But it only needs 4 bytes in this case. In other words, it only needs 1 byte to represent values up to 255, right? Okay, from 0 to 255, you just need 1 single byte to do it. But I can allocate 4 bytes to represent the same value. It's the same thing here. So internal to the assembler, it is allocating 64-bit to each label. But in the context of this instruction, because I'm copying to a 32-bit register, so only the least significant 32-bit is important because the most significant 32-bit cannot be copied anyway.
So if you had a really long program, then this might not work because you might be chopping.
It is
off.
not possible because this is a 32-bit architecture. So that means an address can only be a value that can be represented by 32-bit.
Okay.
Okay, good question. So are we still doing okay so far? And these are the tiny programs that we should write, or if you, well, I would write if I were to take a program like this, take a class like this, I would write a lot of little programs like these just to make sure that I understand, each instruction, each addressing mode, and each concept that we talk about in the class. Each one doesn't take too much time, but it is important to do it like this. Yep.
In regards to answering the exam questions, kind of the way you represented all the comments, would it be okay to just literally put that in?
Yeah, you can put it. You can just you can just write it on that piece of paper.
Okay.
If you think you might need additional paper, you can just bring your binder paper, staple it with your answer.
Okay. But as far as the way you answered in the comments, will that make sense to you and be able, in case like you were saying?
You have to write it in a way that I can understand, because if you just give me a whole bunch of numbers, I don't know the context of the number. So you still have to kind of use a particular way, like this is L1 minus 12, L1 minus 11, and so on. So I can tell what is this byte is at that location, this byte is at that location.
Or at least that's what we think is at that location.
Right.
Okay.
Yep.
All right.
Okay. So are we still doing okay so far with the test question of exam 1? The one and only. Because we are moving a little bit slower than usual to this year. I think it has to do with having more people in the class. All right. So now we can get back to adding, and remember the add instruction is not going to be in the exam. So this is going to be in exam 2. All right. So last time, we talked about all of these topics from 3.1 up to 3.4. So we'll go ahead and just to look at this slide again and see if you guys have any questions about this slide. It really is, this is the symbolic representation of this picture here. Any questions about that? Okay, no questions. If there are no questions about this, then we are going to move into something that is very important. An ALU uses the same width for the operand as and the sum of an addition in operation. So that means if you're adding two 32-bit number, the result is going to be 32-bit. If you're adding two 8-bit numbers, the result is going to be an 8-bit number. If you're adding two 16-bit number, the result is going to be a 16-bit number. So what do we do with that one extra carry from the most significant bits? It has nowhere to go except to be stored and be named the carry flag. Is that okay? So to do, okay. So this bit is not stored in the destination. It is only known as a carry flag, and it is available to you, but only using certain specific instructions. It is latched in an ALU, which means it is going to be available until the next instruction that can change the carry flag. There are instructions that can change the carry flag, and there are instructions that cannot change the carry flag. Okay, so we'll talk about those a little bit later. Next slide. So this is asking, is the answer, is the result, actually 0? This is not the proper way to represent it. Let me see if I can find a better way to look at this one here. The PDF may work better because it has the right encoding. Let me take a look. Yep. No. Nope, that's not any better. The bar should extend over the entire top. Let me see if I can magnify this. Let's get magnification.
Bottom right corner, just.
Yeah, it's not, this bar should be over the entire expression, but it's not showing it that way.
What does the bar mean again?
The bar means negation. Okay, I'm just going to go with this, and I'll rewrite it, using a text editor. Okay, so if I use I don't have a text editor open, so just open one. Okay, back to the notes, and then back to the editor. Okay, so the Z flag is basically the negation of, in this case, the bit 0 of the sum, or bit 1 of the sum, or bit 2 of the sum, or blah blah blah, and then up to, if we have a 32-bit addition, it's up to the bit 31 of the sum. Okay. What do you think is Z if the result is non-zero? If the result is non-zero, then that big huge disjunction is going to be a 1 or true, right? Because a non-zero number has at least one non-zero bit. And if you take the disjunction or the OR of all the non-zero bits, the result is going to be non-zero, or a 1 in this case. But we have a negation on the outside. What is not 1 or not true? Not true is false, but false is also known as 0 when we look at everything as a binary number. So that means Z is going to be a 0 when the number is non-zero. What if the number itself is 0 itself? How do you represent 0 using 32-bit? You have 32 zeros, right? So what is 0 or 0 or 0 or 0?
0.
It's going to be 0. What is not 0? 1. So that means Z equals 1 if and only if the result of an addition is 0. Is that okay? Okay. So Z being 1 is a confirmation that the result is 0. All right. Let's go ahead and do some exercise. Okay. So we are interested in the carry flag. The carry flag is the carry from the most significant bit that has nowhere to store, and the Z flag is indicating whether a number or the result is 0 or not. So I know we are running out of time, but this is really important because an example can really be helpful to illustrate everything. So I'm just going to do this, okay? 1, 1, 1, 1 plus 0, 0, 0, 1. This is a tricky one. Well, kind of. Not really, really tricky. It is also an important one, too. Okay, 1 plus 1 is a 0 with a carry. 0 plus 0 is a 0. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. 1 plus 0 is a 1. 1 plus 1 is a 0 with a carry. So based on this result, what is the Z flag? The Z flag is a 1 because it is the negation of the OR of all the bits. What is the carry flag? 1. Carry flag is a 1 in this case. Okay, is that working out okay? All right, so I'm gonna stop here because we are running out of time. But to prepare for next Tuesday, you want to kind of go over the exam 1 question that we went over today, which has a lot to do with your homework assignment. And that's what the homework assignment is really about, is to help you study for the exam. And if you have time, go over this entire module, okay? Because what we are going to talk about next would be the representation of negative numbers. Okay, so that's a really confusing topic, if you look at it in a certain way. So read that anyway, and then we'll talk about it on Tuesday.
I just have it. Yeah, I have to.